Hey guys, here's a video to help you through the notes for today, and it involves understanding that triangles can be congruent, not necessarily by having to show all of their corresponding parts congruent like we did the other day, but simply that we can show that all their sides are congruent. So this first postulate we're going to learn is called the side-side-side congruence postulate, and it basically says what I just said. If you have three sides of one triangle congruent to three sides of a second triangle, then the two triangles are congruent. So looking over here, you'll notice there's no markings for any of the angles, just the sides are marked, but that's okay. If side AB is congruent to side SR, so if AB is congruent to side SR, and side BC is congruent to side BC would match up with ST, and CA matches up with TR, well, if that's all true, then what we can say is the two triangles are congruent. So triangle ABC would have to be congruent to, so if we go from A to B, then we have to go from R to S. So it'd be triangle RST. So it's kind of like a shortcut. All you need to show for the two triangles to be congruent is that their three sides match up without having to have any of their angles at all. All right, so let's see how that works. Okay, so the first example there, example 1a, says to decide whether the congruent statement is true. So is triangle JKL actually congruent? Oops, let's get rid of that. Is triangle JKL actually congruent to triangle MKL? So you'll notice we have the 9 matching up with the 9, the 8 matching up with the 8, but yet there's no markings for what LK is. But remember that property we learned last week where the two triangles actually share a side? So we could actually say that LK is congruent to itself by, anybody remember? Very good. I'll assume somebody said it. By the reflexive property. So that really lets us get that middle piece there, that the shared side here, this LK, we could put a little mark there. If LK was 5 for the triangle on the left, well then wouldn't it have to be 5 for the triangle on the right? Right? So it doesn't really matter. We just know that it's the same. So yes, in this example, triangle JKL would be congruent to triangle MKL by side, side, side. That's the new postulate. Okay, how about example B there? Example B shows a mark for WV and for ST, shows a mark for WT and for RT. There's no mark for VT and RS. Well, we would need all three pairs of sides to match up, and I can't use the reflexive property here simply because they're not a shared side. They may look the same. I'm sure most of you look at this and say, oh wait, that seems like it's the same length. But if it's not given to us, if there's no information there and there's no reflexive property or anything like that, then unfortunately we can't assume it. So for B, for 1B, we would say that triangle RST congruent to triangle TVW does not have enough information. Okay, so it says decide whether it's true. So right now I would have to say it's false, simply because I can't prove it. And that's how that works. Okay, so there's three ways to really get a piece of the puzzle. You're going to be looking for, are all the pairs of sides able to be proven congruent? And if so, then you can use side, side, side. So for this part, I'm just going to give you a list of 3 ways you can get a pair of sides congruent for what we know now. So in here, well, first of all, the most obvious one would simply be if it was given. Okay, look back at these pictures. This picture has 2 pieces that are given for each triangle. That's great. That's 2 out of the 3 we would need. This one also had 2 out of 3, and then we had 1 that we were able to get on our own, and that's the reflective property. So that's another option. And this isn't in any particular order. I really probably shouldn't number them. I'll just bullet them like we did on the notes. Okay? These are just ways you can get pieces of the puzzle. And when I say pieces of the puzzle, I mean sides congruent or angles congruent or whatever you need to get the triangles congruent. The ultimate goal, of course, is always going to be to try to get the triangles congruent. Okay? So we could use that, and we could use one a little bit from a while ago, but we also can use the definition of midpoint. And I'll show you an example of that soon. But if you remember, midpoint was when you had a point directly in the middle of a segment. So like if this was the midpoint right here, well then these two little pieces had to be the same. So if our goal is to try to get as many sides congruent as possible, we want to know how to get as many segments congruent as possible. Well, given is a way to get it, reflexive property is a way to get it, and midpoint will get us segments that are congruent as well. Okay, so those are the three of the reasons you could use to get sides congruent in a triangle proof. Okay, let's actually look at a proof. All right, so obviously, I'll just set up my chart here. And sorry I couldn't do this the other way. I don't actually have a printout of this, so I'm just going to have to keep doing it this way. So I have my statements and my reasons. And let's see. Let's start with the given. Right off the bat, they're giving us AB is congruent to CD, and DA is congruent to CB. And that's given. So with that being given, I think it would be a good idea to actually mark our picture. All right, so let's see if I can do this. I'm going to try to mark this on the picture here. I'll just make make a little segment for AB, a little tick mark, and make that a little thicker so you can see it better. There we go. And I'll also match that up. We said that matches up with CD, right? So AB is congruent to CD, that's given, and DA is congruent to CB. So let's do another one here. DA. But I want to use a double tick mark so I don't mix it up with the first one, right? And let's match that up with BC. There we go, that's not too bad. Right, so just to recap again, AB is congruent to CD, that's right here. DA is congruent to CB, that's right there. That's our given, right? Our two statements that are given. And we could write them separately, I guess, or we can put them in one line. But it's not a big deal right now. Let's just get all the pieces of the puzzle. Right now I have two pieces of the puzzle. I need a third. Well, if you remember what we said a moment ago, we have three different ways of getting segments congruent. We've used some of the given already. This particular proof doesn't seem to involve a midpoint. However, there is a shared side, right? See it? AC is shared for both triangles. So technically, I could mark it. Let's see if I can do this on the side here and diagonally. Okay, actually let's get rid of that one. Boop, boop, there we go. All right, so AC is congruent to itself. The way you would do this, you could say AC is congruent to AC, and we've done this already. This isn't actually new, but it's part of the proof now, by the reflexive property. And we are almost there. In the other proofs we did for the last homework, you had to get all the angles also, but what we learned was we don't actually need the angles now. We can use just the three sides. Now we can actually conclude triangle ABC is congruent to triangle CDA because of side, side, side. You could write side, side, side congruence postulate. You could just write side, side, side. That's totally fine, and you're good to go. Okay? Let's do the last proof here. This one, we've got given FJ and HJ. Okay, that's given. Make some space here. Statements, reasons. We've got FJ congruent to HJ, and that's given. We also have G is the midpoint of FH, so that's different. G is the midpoint of FH, and that's going to be obviously our new thing here. That was also given. And I guess we'll just jump right to it. What does that mean? Right? G is the midpoint of FH. If G is the midpoint of FH, that means G is right in the middle, which means FG and HG have to be the same thing. Okay, well, if they have to be the same thing, oops, if they have, oh boy, where did it go? There it is. Sorry. If they have to be the same thing, that means that right here, and I'll need two of them, right? FG and GH literally are the same thing, so I can mark them the same. And that's a piece of your puzzle. All right, you could actually write FG is congruent to HG, and what you would use is, if you remember from what we wrote a moment ago, we would use the definition of midpoint. That's what a midpoint is. From way back in chapter 1. Definition of midpoint. Now let's take a look. How many pieces of the puzzle do we have? We're trying to get these two triangles congruent. I have 1, 2, 1, 2. I still need a third. Hopefully you see it. You see that JG is shared by both. So in fact, that is one of our steps. JG is congruent to JG. And of course, that's the reflexive property. And now it looks like we have all the pieces of the puzzle. We have 1, 2, and let's see if I can get a 3 on here. Actually, just get one of these here. This would have been much easier if I had it printed out. Bear with me. 2, 3. And there it is. All right, not too bad. And since I have all three pieces of one triangle, all three sides of one triangle congruent to the other, I can then conclude triangle FGJ must be congruent to triangle HGJ. And of course, that's by our new postulate side, side, side. So getting the pieces of the puzzle is what you need to be able to do. And that could be done using what's given, using the reflective property, using the definition of midpoint. And that's all you really need for now as far as doing the proofs. Okay? And the last type of example you're going to see is this one's not, this one's more familiar, I would assume, because it deals with the coordinates. And all you have to do here is literally find all the lengths. Okay? So determine whether the triangles are congruent, or if there are any triangles that are congruent to PQR. You just simply need to get all the lengths, right? So you would literally count, PQ you can count because it's just vertical. QR you can count because it's just horizontal. And then how would you do PR? Right? We'd have to use the distance formula for that. So let me just remind you of the distance formula, and that should help out with that. So distance formula. There you go. And that'll get you any of the distances that aren't just vertical or horizontal. So like PQ, you don't need to do the distance formula for PQ, right? Just count the boxes. It looks like 3. How about QR? QR, you don't have to count the boxes. You just count, I'm sorry, you don't have to do the distance formula. Just count horizontally. 1, what's that? My eyes are bugging out here. 1, 2, 3, 4, 5, it looks like. There's 5. And then, of course, PR, you could figure out using the distance formula. So I'll do this one for you just to get you started. And then you can determine if, in fact, they actually are the same. So PR, let's get the coordinates for P. So -3, 1, 2, 3, 4, 5. P is -3, 5. And R is, where's that? 2, 2 it looks like. So then PR would be, let's see, it's going to be 2 minus -3 and 2 minus 5. So that's 5 squared and -3 squared. So that's 25. Oop, I ran out of room. Hang on, I'll zoom out here. That is 25 plus 9, which is the square root of 34. Okay, so you would just put that. You don't need the decimal for that. You could just write square root of 34. Because remember what you're looking for. You're literally looking for, do I have, 3, 5, and square root of 34 on any of these two triangles? If you do, well, then they match up. So that's what you're looking for. And I'll kind of leave it there. I feel like that's probably enough to get you started. Please feel free to post any questions or ask any questions. And good luck with everything. And I'll see you guys soon.